Section 11.5 is on lines and planes in space. Our objectives are to write a set of parametric equations for a line in space, write a linear equation to represent a plane in space, sketch the plane given by a linear equation, and find the distances between points, planes, and lines in space. Term 11.1 is parametric equations of a line in space. A line L is parallel to a vector v with components a, b, and c, and passing through the point P with coordinates x1, y1, and z1 is represented by the parametric equations. X is equal to x sub 1, which is the point on the line, and plus AT, where A is the first component of your parallel vector. Y equals y sub 1 plus bt, and z equals z sub 1 plus ct. So you need two things in order to determine the parametric equations for a line in space. You need a single point on the line, and you need a vector that is parallel to the line. You can eliminate the t's in each of these equations, solve each one of these for t, and equate the t's to get symmetric equations. These are both ways to represent lines in space. Very different than how we represented lines in a two-dimensional graph where we had y equals mx plus b or ax plus by equals c. To represent a line in space, you either use parametric equations or symmetric equations. Suppose we want to find parametric and symmetric equations of the line L that passes through the point 1, negative 2, 4, and is parallel to the vector v with components 2, 4, negative 4. You need two things to determine the equations for a line in space. You need a point and a parallel vector. For this example, you're given both. So our solution in finding the parametric equations, we have x equals 1, that's the first coordinate, 1 plus 2t. We get the 1 from the point, we get the 2 from the vector. Your x equals 1 plus 2t, your y equals negative 2 plus 4t, and z equals 4 minus 4t. Solve each one of those for t and equate them to get the symmetric equations. X minus 1 divided by 2 equals y plus 2 divided by 4, and z minus 4 divided by negative 4. Here's an additional example. Find parametric and symmetric equations of the line that passes through the point 2, 2, 1 and is parallel to the parallel to the vector negative 3, 0, 1. To find parametric equations for a line, you need the point, you need a point with coordinates x1, y1, and z1, and you need a vector that is parallel with components a, b, and c. So the parametric equations would be the x value that's on the point plus at, y equals y sub 1 plus bt, and z equals z sub 1 plus ct. Plugging in the information we're given, x1 is our positive 2, 2 minus, we use the a from the vector, minus 3t, 2 minus 3t. Y is equal to the y from the point, 2 plus the b from the vector, 0t, and z equals 1 plus 1t. And of course you can simplify those, but that essentially are these essentially are the parametric equations for the line. find the parametric equations, we solve each one of these for t. You can solve this for t by subtracting 2 from both sides, and you get x minus 2 equals a negative 3t. And by dividing both sides by negative 3, you get t is equal to x minus 2 divided by negative 3. Now for the y, this simplifies to y equals 2. Notice that you can't solve for t in that equation. We can use that as a separate part of the parametric equations, symmetric equations. Now let's solve the last one for t by subtracting 1 from both sides. You get z minus 1 equals t. So we're going to let the t from the x part of the parametric equations equal to the t for the z part of the parametric equations. Set those to be equal to get x minus 2 over negative 3 equals z minus 1. And then that other part of the symmetric equations will have to include the restriction for y. So that would be our symmetric equations. I'll abbreviate it with an SE. And what we have listed here are the parametric equations. The second example we want to find a point on the line and a vector that is parallel to the given line. And here we're given the parametric equations. X equals 2 minus 3t, y equals 2, and z equals 1 minus t. One thing we can do is determine some points on the line. For example, where is the point? What is the position of the point in space when t is equal to 0? When t is equal to 0, you plug t into the parametric equations, and you have x equals 2, y equals 2, and z equals 1. So the one point on the line given by these parametric equations, the point is 2, 2, 1. That's a point that's on the line, and that is the point that corresponds to the time equals 0. Suppose we let t equals 1. What location is the point on the line? If you let t equal 1 and you plug it in here, you get 2 minus 3, which is negative 1, y is equal to 2, and z is equal to 0. So the point that corresponds to when t equals 1 is negative 1, 2, 0. So these are both points on the line. So you can give either one of those as a point on the line. And to find a vector that is parallel to the line, let's use the 2 points, P and Q. Those are both on the line. If we find a vector PQ, that vector is going to be parallel to the line. So the components of that parallel vector would be negative 1 minus 2, negative 3, 2 minus 2 is 0, and 0 minus 1 is negative 1. So we actually found 2 points on the line, and we found a vector that is parallel to the line. Now this is not unique. There's an infinite number of points on the line, as well as an infinite number of vectors that are parallel to the line. This slide offers one solution. For this example, we want to find parametric equations of the line through the points 2, 0, 1, and 1, 4, negative 3. To find parametric equations, you need one single point and you need a vector. So let's use the 2 points that are on the line, call them point P and point Q, to come up with a vector that is parallel to the line. PQ, the PQ vector is the vector that's parallel to the line. So let's find the components by taking the terminal point and subtracting the initial point. 1 minus 2, you get negative 1. 4 minus 0, 4, and negative 3 minus 1, you get negative 4. This is a vector that is parallel to the line, so that's going to be your vector with components a, b, and c. And then the parametric equations for the line would be x equals some starting x plus at, y equals some starting y sub 1 plus bt, and then z equals some point on the line z1 plus ct. You can plug in the known. We could use either one of these points, P or Q. I'm going to go ahead and use the points P. So that's your x1, y1, and z1. And you will have x equals 2 plus a, which is the component on the vector, negative 1 t. Y equals y sub 1, which is 0, plus bt, where b is 4. And z equals z sub 1, which is 1, plus ct is a negative 4t. And of course you can simplify this to get x equals 2 minus t, y equals 4t, and z equals 1 minus 4t.